Visible light is a narrow band of radiation within the electromagnetic spectrum which illuminates our world and the cosmos. The nature of light had been a mystery for thousands of years. Theories about its essence ranged from showers of particles to waves. Some ancient Greek scientists believed that light traveled from a luminous body to the eye in a stream of very fine particles, while others taught that light is some kind of high-speed wave-like disturbance. The Greeks knew that light travels in a straight line and had formulated the inverse square law, stating that the intensity of light decreases with the square of the distance. And they knew about the law of incidence, which states that when light is reflected, the angle of incidence is equal to the angle of reflection. Galileo hoped to discover whether light traveled instantaneously or with finite speed. Trying to determine the time light took to travel to a distant mirror and back, Galileo found the interval, if there was one, too short to measure. It wasn't until the end of the 17th century that the speed of light was correctly determined to be around 186,000 miles per second. The speed of light is one of the most important constants in physics. The Dutch scientist Christian Huygens is known as the father of the wave theory of light. His theory states that any point on a wavefront may be regarded as a new point source of waves. This principle is important in explaining diffraction, or the bending of light around obstacles, a powerful indicator of the wave nature of light. In 1862, James Clerk Maxwell announced that light is energy carried in the electric and magnetic fields of electromagnetic waves. However, Maxwell's brilliant synthesis of the laws of electricity and magnetism was not the last word on the mysterious nature of light. Around the turn of this century, a great revolution in scientific thinking was taking place. A theory known as quantum mechanics was elaborated upon by Albert Einstein. He asserted that light consisted of tiny packets or bundles of electromagnetic radiation called photons. One of the most significant properties of the electromagnetic wave is that it transports energy. Light from even the nearest star beyond the sun travels many billions of miles to reach the Earth. Yet it still carries energy to stimulate the electrons within your eye. Light is emitted by electrons moving from a higher to a lower energy state. This energy, which we perceive as light, is released in the form of photons. Experiments like this one are designed to demonstrate the particle nature of light. A special type of light source, shielded from ambient light, is targeted towards an instrument called a photomultiplier. The light beam is considerably attenuated to a level below our ability to perceive it, which reduces the flow of photons to a number that can be counted. A motor drives the photomultiplier across the target area, very slowly scanning the dimmed light beam. A computer is programmed to give a statistical sampling of the photons at set intervals. Incredibly, we can actually hear these particles strike the photon-sensitive plates within the photomultiplier. The computer is recording the number of particles in the light beam. The distribution curve demonstrates the wave field in which these particles are carried. Fewer photons at the wave trough, growing in number as the wave peaks. The theory of quantum mechanics liberated many physicists from the seemingly irreconcilable differences in the behavior of light, providing them with a unifying explanation for both its particle and wave manifestations. So we now know that light is radiant energy transported in photons that are guided along their path by a wave field. In unraveling the nature of light, we find that white light from the sun or from a common lamp is incoherent. That is, photons of many frequencies and phases are released. White incoherent light is chaotic. Its beam gets wider and less intense with distance. This type of light is actually a composite of all visible frequencies. The colors we see depend on the frequency of the light emitted. Due to the wave nature of light, a prism can bend a beam of light, with the shorter wavelengths being bent more than the longer wavelengths, so that the full frequency range is displayed. The lowest visible frequency is red. The highest is violet. Between them are the infinite number of hues that make up the color spectrum of the rainbow. The color of an object usually depends on the color of the light that it transmits, absorbs, or reflects. Most of the objects around us are non-emitters. They reflect light rather than emit it. Color is a property of the light that reaches our eyes. The world around us is filled with a vast amount of electromagnetic radiation that stimulates the sensation of color when the vibrations interact with the cone-shaped receiving antennas in our retinas. Lasers generate beams of coherent light. In other words, a beam of photons having the same frequency, phase, and direction. First built in 1960, within a decade, laser beams spanned the frequency range from infrared to ultraviolet. Besides an ever-widening range of commercial and scientific applications, lasers provide us with an excellent incident beam for demonstrating much of the phenomena associated with wave behavior. By adjusting, inserting, or replacing certain optical components, we can use this same laser beam to observe reflection, refraction, diffraction, interference, and holography. Let's start with reflection. Here, the laser beam is directed towards a mirror. We see the incident beam reflected off the surface of the mirror at an angle equal to the angle at which it strikes it. The other beams are just secondary reflections in the mirror. If we rotate a mirror so that the incident beam is constantly being moved, we see that the reflected beam moves in tandem with the incident beam. These two angles will always be equal. The angle of reflection is always equal to the angle of incidence. This law is true for all wave motion. When the laser beam is passed through mediums of different propagation speed, we discover another interesting property of waves called refraction. Refraction is the bending of a wave as it passes obliquely from one medium to another. Refraction occurs because of a change in the speed of the wave. In this example, light is passing from air into glass. This lens is flat on one side and convex on the other. As the laser beam is moved across the flat side of the lens, we can see how the angle of refraction varies with the angle of incidence. Using this projector as a white light source, and a prism that will refract the light beam as it passes from air into the glass, we can separate the light into its component frequencies. In glass, As with all dispersive mediums, the frequency of the wave determines its refraction index. Each color represents a particular wavelength, which refracts differently from other frequencies. Because of this, the light rays disperse as they exit the prism. Instead of dispersing adjacent wavelengths, what would happen if we caused them to cross or interfere? To demonstrate this, we return to using the laser as our incident beam and introduce an instrument called an interferometer. This first unit acts as a beam splitter, dividing the laser rays into approximately 2 halves. The second unit recombines the incident beam by superimposing the wavelengths. This creates something called an interference pattern, or fringes. When the output beam is shown against a screen, this is the effect. Interference is the superpositioning of waves, producing regions of cancellation and regions of reinforcement. Constructive interference refers to the brighter areas where wave crests coincide. Destructive interference refers to the darkened areas where a wave crest is canceled by an overlapping wave trough. By tilting one of the beam splitters, an angle is created. Manipulating this angle allows us to create interference fringes in any direction. By changing the ambient temperature of an area within one of the beam paths, we change the index of refraction. Here, dry ice cools the air. Since cooler air is more dense, light travels slower through it than through the surrounding warmer air. We can see the interference patterns produced by introducing the dry ice. A match will warm the ambient air, making it less dense than the surrounding air, allowing the light to travel faster. A soldering iron generates heat waves, and the effect is similar to that of the match. In both of these cases, part of the light has been refracted, so that when it is superpositioned with the rest of the beam, the waves are interfering. The light passing through this water-filled vial will refract uniformly. But as salt is introduced, the water immediately surrounding the crystals becomes more dense, and its index of refraction differs from the rest of the water, creating a new interference pattern. Interference and a closely related wave property called diffraction provide the best evidence of light's wave-like nature. We know that by and large light travels in straight lines, but light, or any wave motion for that matter, can be bent around obstacles. This bending is called diffraction. As light passes through a narrow slit, it diffracts into primary and secondary wave fronts of decreasing intensity. When light spreads into a region behind an obstruction, it is said to diffract. Remembering Huygens' principle that any point on a wave front can be regarded as a point source for new wave motion, we can create new wave fronts by passing waves through a narrow opening. The narrower the slit, the greater the bending of the waves at the edges. The amount of diffraction also depends on the wavelength of the wave. We can produce different diffraction patterns by selectively eliminating certain components. For example, light from vertical lines is dispersed horizontally, and light from horizontal lines is dispersed vertically. A transmission grating placed in the path of the light waves disturbs the wave fronts because the grating is opaque, while the narrow slits between the lines are transparent. In a sense, Interference and diffraction are two sides of the same coin. Interference refers to the superimposing of waves so that the effect is either a loss of intensity or a reinforcement. Where these effects occur, we can see interference patterns. In diffraction, new waves are formed by the bending of light around an obstruction. The resulting wave motion creates areas of varying intensity. Perhaps the most exciting illustration of both interference and diffraction is holography. Holography would not be possible without the invention of the laser. No image-forming lens is used. Instead, the image captured on a light-sensitive plate is a recording of the interference patterns of two sets of wavefronts. One set of wavefronts is from light reflected by the object. The other set of wavefronts is from the reference beam, which is diverted from the illuminating beam by a mirror. The recorded image is called a hologram, from two Greek words meaning whole message. And a hologram is just that. Unlike a film negative, a hologram's image is contained in every part of the plate. You can cut it over and over again and still be able to reproduce the entire image. No visible image exists on a hologram. It is a mixture of swirled lines and fringe areas of varying density. Basically, the hologram is a photograph of tiny interference patterns. A hologram must be viewed in laser light. The plate acts as a complex diffraction grating, and a remarkable image is reproduced in 3 dimensions. An ocean wave has both longitudinal and transverse characteristics. We know that photons are propagated in a wave field. But what is the vibratory motion of the wave? Is it longitudinal or along the direction of propagation? Or is it transverse, perpendicular to the wave direction? The fact that light waves can be polarized demonstrates that they are transverse. Polarization is a property of transverse waves. Waves traveling along the direction of propagation are confined to either the vertical or horizontal plane and are said to be plane polarized. Light is polarized when the electric vectors of the electromagnetic radiation are aligned. Polarized light is often used to test for stress. Here an object is placed in the pathway of polarized light, and where the intensity of the light varies due to non-uniformities in the substance, stress points are revealed. Light is a unique form of electromagnetic radiation in that the energy it releases illuminates our universe. Though we have only recently been able to unravel some of the mysteries that surround the nature of light, its essence has been the object of speculation for thousands of years. And its exact nature still remains elusive.